Light is a messenger. And it brings to us information about the properties of objects that emitted. What information we can retrieve? We discussed a couple of things. For example, we discussed various kinds of spectra. Essentially, emission, line spectrum, absorption line spectrum, and continuous spectrum. So these are main kind of light which comes from objects, specifically from stars, and they have various information in them. So what we learned is that these guys and how they are produced, that we discussed in Kirchhoff's laws. Then the last one is continuous spectrum. How they are described, which one will be produced, is summarized in Kirchhoff's laws. And these guys, they have information about the chemical composition of objects emitting them. Because of this, so they essentially are markers of atomic structure. One should really think of them as like ISBN codes of molecules and atoms. So we have this information, and then on top, continuous emission spectrum. This is described using Planck's distribution or Planck's law, which contains in it these two sub-laws, Wien's law, which tells you where is the peak intensity, and Stefan Boltzmann law, which tells you how much power is emitted. So this continuous spectrum and Planck's distribution, they are related to heated objects. So they are produced because of thermal radiation. When you heat an object, they emit a continuous spectrum and is described by Planck's distribution. You can read off temperature remotely by using Wien laws. And this is just observing which wavelength. When we say wavelength is equivalent as saying as frequency, because they're tied together. Which wavelength, by observing which wavelength has most power. So if I draw power here, wavelengths here, there's some peak. And that translates, tells us what must be the temperature of the body emitting it. And once you know the temperature, Stephen-Boltzmann law also tells you how much is the power coming out. So these then give us handle. So we can use these to find temperatures of stars and knowing the distance also the size of the star. Because size is related to total power coming out. And power is related to how far the star is. Well, maybe I should mention that we also discussed apparent brightness, which we see on Earth, and luminosity, which is the inherent power, total power. So apparent brightness, we discussed this relation goes down as the square of the distance because it just spreads out. So knowing the distance, knowing the apparent brightness, we can compute the luminosity, total power, and this Stephen-Boltzmann law gives you power per unit area. So using all these, we can find the total area. Then we also discussed that we can find the speeds of objects using line spectra, which was essentially how the lines shift, red shift and blue shift. Unfortunately, the most interesting application of this red shift, we haven't been able to discuss this. I just don't know how we left behind so much. We also lost some classes, but it's a pity we couldn't discuss cosmology. There's a big application of this and that. In any case, what we have studied that we can find the speeds of objects remotely. We don't have to go there and do anything. So we know the speeds of stars, and we also learned, so this is Doppler's shift, both of them. And we also discussed how to measure the masses of stars. And that was using Kepler's third law in binary star systems. If it's a binary star, or if you can find some object, find any object orbiting a star. So that then gives you how to measure the mass using the Kepler's third law. Just give me a minute. Newton's form, which basically told us that the constant over there in the Kepler's third law depends on the mass of the orbiting objects. Then we said, like, since we can get all this information about stars, organize the information in a chart diagram. Wait. It was essentially plotting the, by the way, when we said organizing the information in a chart diagram, which is plot of surface temperatures of stars against luminosity. So luminosity, how luminous a star is, we classified them in luminosity classes. And the temperatures, we classified them into the spectral classes. And we also had this magnitude system, which is related to apparent brightness. So luminosity classes were um, 5 classes, then apart from that you had the, well, apart from that you had a special class, white dwarf, and then you had spectral classes in terms of O, B, F, G, H, I, those things. Using these, we made a plot which gave us, so temperature goes this way, luminosity goes this way, logarithmic plot. This gave us the these patterns of main sequence, most of the stars here, and some stars here, the red giants, some stars here, the white dwarfs, and there were some things over here in stability strip. And using these, we had some kind of idea what kind of stars are there and what are their general properties, what is the range of their properties, what kind of temperatures they can have, what kind of sizes they can have. Sizes were also hidden here. Also hidden in HR diagram. So we got some kind of patterns that what are the ranges of temperatures, luminosity, sizes, and ages of the stars. And then we try to explain, based on this, we try to form a model of stars. So after discussing all this, we discussed life cycles of stars. So we learned that the stars are born, how, and why. Well, they're born in from interstellar dust and clouds, which are mostly hydrogen, some helium. Why? Because gravity attracts. So if you have anything lying in space, it's going to contract. Clouds makes the clouds contract. Clouds shrink under gravity. And the governing principle over here was which you can also say the physics behind it. The virial theorem, which is just a form of third law of Kepler. Which said that as you contract, you heat up, And as you heat up, you radiate more light or more radiation, more energy. This is just Stefan Boltzmann law. But the most important part was, as you radiate, you must contract more. Because this is like, because this is like a light source connected to a hydro power dam. As you heat up, you have to give off light. Where does that light come from? Like a hydropower dam, something falls. Something falls and gravitational potential energy is used to supply for the radiation. But as you lose, so as a result, this makes it a one-way process. You keep radiating, you keep contracting. As you contract, you heat up, you radiate more, you contract more. But a star is born when the core of the cloud is heated to about 10 million degree Kelvin. At this point, we said nuclear fusions are set in. So proper life of a star, which we call the main sequence lifetime. So all the stars on the main sequence on HR diagram are going through this proper life. This occurs, this corresponds to when energy source for star luminosity is not gravity but nuclear fusion. And then we studied, and then when this happens, contraction stops, and we have a stable size and stable luminosity. Let me just mention it here, although it's just a review. I didn't mention it during the class that the size and luminosity is stable, but not completely stable. There are changes over the lifetime of a star where this luminosity slowly increases because the core is still slowly shrinking a little bit. The reason is again because you are running out of fuel, and so that's why the sun in the past was less bright compared to now. And over time, its brightness is slowly increasing, but this is a very slow change. Anyway, so pretty much stable size and stable luminosity. Then we discussed basic nuclear physics. How does this happen? We need high temperatures for nuclei to fuse. Nuclear fusion, main thing we learned is that you can combine various nuclei to make bigger nuclei. And in this process, typically, neutrinos are produced. We discussed what are these and their properties. And this graph of nuclear binding energy, you can say it's like the potential energy for nuclei. And over here, atomic mass. So we learned if we combine nuclei, we are lowering their binding energy per nucleon. So something comes out, energy comes out over here. While over here, if we break a heavy nuclei, again binding energy per nucleon goes down. So something can come out here. So you can get energy through fusion. Fusion and energy to fission, which is essentially breaking up a big nucleus. There is this valley point, which is iron. You do anything to it, you can get energy out, you have to provide energy. So in stars, it's this process which is important and actually the very first step of it. For the main sequence lifetime, it's just going from hydrogen to helium, which is important. Then we discussed that there is an end to stars enter old age and die. This happens because you run out of fuel. Fuel is just hydrogen So when the fuel runs out, then something has to give. And we studied the process of aging, which was essentially so process of aging is that nuclear reactions stop in the core. Why do they stop? Just because you have run out of fuel. And that means the core again relies on gravity to provide energy and shrinks. Just like uh, again you have a hydroelectric system, hydropower system going on. Something is falling, and that is energy. So what you get is you first have the core is now made up of helium, your temperatures rise, and the core again starts burning, and it's surrounded by hydrogen. Helium then burns out very quickly because now you're burning at a higher temperature, so you give off lots of light, and to keep up that you have to burn a lot of helium. So this burns out, and you have a carbon inside, helium outside, and hydrogen. But at this stage, what happens is, one should remember, is that star acts like hot air balloon. The outer surfaces go in opposite direction to the core. What do I mean by opposite direction? I shouldn't say opposite direction. Uh, in terms of temperature and size. Yeah, when the helium burns out, helium when it combines, helium is combining to make heavier nuclei, and the heavier nuclei the helium makes is the carbon. So that's why helium is depositing carbon in the core, and once the helium is all burnt out, what is left inside is the carbon. But it's surrounded by helium. So in the outside, where the temperatures outside, where the densities are not that high, the helium is still burning. And if you go even further out, where the densities are still a bit less, there's still some hydrogen burning. Collected from the top layers into it, fallen into it, because this core is now extremely heavy. So some burning is happening in the shells. But it's a hot air balloon. So as the core goes up in temperature, core shrinks, goes up in temperature, that inflates the balloon. Shrinking core with its rising temperature and extreme luminosity, because it's now at a very high temperature, so it gives off too much light, way too much light. Inflates the balloon. And then it's just like in regular balloon, as it inflates, the outer layers, they become large, and as something expands, it cools down the outer layers. So if you see a star which is whose outer layers are cooled down, that doesn't mean that the internal core would also be cool. The internal core may be actually much hotter. So if the cooling is because of the large size, that means that there is some energy source inside which has inflated the outer layers. So if the outer layers are very, very large, they have big size, then you can be sure that the core inside is extremely hot now. So they go in the opposite direction. But if the outer layers are small, then it's probably a normal main sequence star. And if it's cold, then the core is also cold. And it's cold because there's not much mass in the star to heat it up. So this stage, this old age, there's more detail to it, which you can see in the lectures. I'm not doing everything. This old age is called the red giant stage, because the outer layers have inflated, so they're giant, and they've cooled down, so they are wet. But this is true. And the depth, what is the depth? Outer layers are finally and slowly blown away. Because obviously they have been inflated, so there's not much which is keeping them together. There's lots of light pressure from inside, so it just blows it out. And the corpse, what is the corpse of the star? Corpse is just the inner core revealed. And what is this? This is just carbon, which is not burning. Since it's core, so it's small in size, has no energy source, because it's not burning, and it's made up of carbon. But it's extremely hot. Because it has crossed helium burning temperatures. By the way, whenever I say burn here, it's not chemical burning. I'm talking about nuclear burning, which occurs at very high temperatures. So it's very hot, and it's very small in size. So this is called white because it's hot, and dark because it's small. And it's just cooling away. Then we discussed that it doesn't shrink, because if it shrank, it would heat up even further. It won't cool away. The Wheel theorem would say that it will shrink and it will heat up. It doesn't shrink and heat up because of degeneracy pressure and Chandrasekhar limit tells us the maximum mass of this object. This can have and this degeneracy pressure also explained why we need a certain minimum mass to make stars. It also explained why above a certain mass a star must be born. Because if the cloud is too light, then the degeneracy pressure becomes significant enough before nuclear reactions can set in, and degeneracy pressure can stop the collapse under gravity. Degeneracy pressure is something which fights gravity. So in lighter clouds where there's not much gravity, the degeneracy pressure becomes large enough quickly so that you achieve stabilization before nuclear furnace can be ignited. While in larger clouds, the gravity is large enough and degeneracy pressure does not become significant enough before the nuclear furnace is ignited. But even in these larger clouds, in the final states, when the nuclear furnace has gone bunk, it sets in and gives you the white dwarfs. Then finally, we said that there is a twist in this story. When if the star is very heavy. Heavy. How heavy? If it's greater than 12 solar masses. Then what happens? Then core is very heavy. Well, the whole star is so heavy. Heavy that degeneracy pressure cannot stop the shrinking of carbon core before it crosses, let's say, 500 million Kelvin. In other words, before it crosses the temperatures required to burn carbon. Carbon didn't burn here. I said it is not burning. Why it's not burning? Because the degeneracy pressure, to burn, it needed higher temperatures. And to reach higher temperature, it had to shrink further. But the degeneracy pressure had stopped the shrinking. So it couldn't heat up itself to reach the temperatures required for the burning of carbon. But in the heavy stars, the weight is so much, the crushing is so much that it does happen. So all elements that can be produced and burned to give energy are produced and burned. Over here, you first are burning hydrogen, then you run out of that, you burn helium, you run out of that, you burn carbon, you run out of that, you burn oxygen, you run out of that, you burn silica, and so on. You keep going until you reach iron. Iron cannot burn and it has nothing to do with degeneracy pressure. It just doesn't give you energy. It's in the valley. Iron core just cannot give energy. So when iron core is there, and if the mass of core increases more than Chandrasekhar limit, the core completely collapses. So Chandrasekhar limit says that this is the limit where the degeneracy pressure completely fails. It can't do anything. So core turns into bunch into a blob of neutrons. So the core turns into a blob of neutrons, and huge amount of energy is in release. And a supernova is born. And neutrinos in huge number come out. The supernova is like a big explosion. So big stars die big in an explosion, while small stars, they just fade away. The core turns into a blob of neutrons because the Chandrasekhar limit says that the degeneracy pressure just cannot stop it. So the result of this is that the protons and electrons, which are normally separated, they are fused. So this reaction, which we had studied many times in the class, and we had said that you can move them to the other side of the equation. This occurs. So protons and electrons, you can say that they are crushed into each other and they form neutrons and neutrinos. Neutrinos fly away. And there's this light. You can say this is just energy which is produced. And you are just, all the atoms are converted into neutrons. And neutrons are all then just bound together through nuclear forces. So you get a new kind of object which is a blob of neutrons. And actually this is now held together. It's not, it's the blob attains a stable size because the Chandrasekhar limit for the neutron blob is bigger. For neutron blob is bigger. So it doesn't have to collapse, it just stays together a stable size because of its own degeneracy pressure. Degeneracy pressure increases very high if you have very dense object. So this object is very dense, extremely dense. 100 billion tons in a quarter of a teaspoon. That's how dense it is. And this blob is seen as a pulsar in the sky, which we also call the neutron star. And these pulses are radio pulses observed on Earth. Very highly timed, so it's like beep, 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 as if someone is sending a signal. Yeah, so we couldn't discuss black hole. I just cannot. I'm really disappointed because the course just took a very different turn after the midterm. And also we were a bit slow before the midterm, so we couldn't discuss all the things which we wanted to, which I usually discuss in this course, and we always happen to complete it. This time, I don't know what really happened. But answering your question, how the black hole is formed, it's again a possibility. So I said you got a neutron star because it has a higher Chandrasekhar limit. Its Chandrasekhar limit is close to about 3 solar masses. So if your core was 1.2, when it crossed 1.2 solar masses, the Chandrasekhar limit for electrons was reached and it collapsed into neutron star in a supernova. But imagine, and it has its own degeneracy pressure, but it has its own Chandrasekhar limit, which is 3 solar masses, a little less than 3. Imagine you keep piling up more matter into some neutron star. Maybe there's neutron star, and maybe there's some gas around it, which is falling into it, or something like that. Or for some reason, the core was way too heavy. Then what will happen? The neutron will also collapse. And where will they go? So we think that they just disappear. There's nothing now to stop them. Neutrons cannot turn into any other thing which will have a higher Chandrasekhar limit. And they collapse into forming a black hole, which is just like everything, all the mass on one point. Yeah, so the black holes are also can be a final outcome of collapse of a star. But these two possibilities, neutron star and white dwarfs, they are much, much more on solid footing in the sense that we have seen them. Well, we have now also seen the black holes. We are at least very confident. Black hole, in some sense, you can never be sure. It's such a thing which you can never be sure about, but we are very confident. For neutron stars, they have certain properties which you can predict and you can observe from Earth, which is what we observe in case of pulsars. So that's the whole story about stars. I have essentially summarized all what we did so that you can at least have some idea what we discussed. Okay, so any question or should I stop here? Okay, let me stop. Bye bye.